Okay, so in the tutorial classes, what we have planned, we are going to give you questions, and you or in a group, you try to solve the question. There will be some questions which can be solvable. There may be some questions which may not be solvable, right? Not solved yet. It may be solvable. Okay. And once you find solution, you can discuss with us, or you can come and solve for all, right? So for today's thing, we have listed like 1 2 3 like that, the order. In a pen you can see that the level of difficulty is there, so accordingly you try to solve. So if you want me, then I can write the question. Right, so you can see this question. So it is already written using greedy coloring so that every planar graph is 6 colorable. It's trivial, right? Every planar graph is 6, right? Yes. Can we get a proof? We know planar graphs are 4 colorable also, but we want whether we can get a 6 coloring of planar graph. Yeah.
Using induction, 4 and less than or equal to 5, it is trivial true. And assuming the base case true and let G be a graph on n plus 1 vertex, we can have an ordinance that Bn has only 5 neighbor previous to. Using the theorem.
Yeah. So you want to tell that planar graphs are 5 degenerate, right? Then by using the ordering of this thing, we can apply the greedy algorithm, and we can say that it is 6 colorable, right? Already done this thing in the class in the morning, that if k degenerate graph is there, then it is k plus 1 colorable. Second questions already done. Double critical graph is critical, right? Everybody, right? So have you heard of this thing, Cartesian product of graphs? So let me define for you Cartesian product of graphs. Product of G and H, right? How it is defined? So the vertex set of this thing is you take the Cartesian product of vertex set of this thing, and what is S set of this is so these are basically you take like you define like this. Let us take U and V, and U dash V dash are adjacent, right? If so, first coordinate if they are equal in the first coordinate, they have to be adjacent in the second coordinate, right? If U is equal to U dash and V dash is an edge of H, or U dash is an edge of the graph G, and V is equal to V dash, right? So what is the meaning of this one? Let us try to have P2, and if you take GH same, then how it will look like? What will be Cartesian product? Let us say this is G, this is H, then it will be like right. So can we let us try to see another little bit. Let us say this is our G and H is this is H. And how it will look like? G, this is G. For every, oh yeah, so it will be like right, okay. So what is the meaning of this one? So here if you see, right, and here you try to see, so what is happening? So here each vertex of G is replaced by a H, by a copy of H, right, and they are adjacent, the similar thing are adjacent, right. Okay, so here we need to know what is a chromatic number of this thing. Now, what will be chromatic number of this thing? Because G is sitting, H is sitting, so it will be definitely greater than chi of G, and also it is greater than chi of H. So these two we can say that it is greater than equal to max of chi G and chi of H, right? Okay. So what about this? Whether this is exactly equal to, this is my question. So you try to solve this, try to see this is easy.
When you will finish?
5:30.
5:30, okay.
Yeah, I'll wait till 5:30 and then we'll go to.
And that's at 6.
So which slide you are going to? The slide you send me?
Yeah, it's like
That is a very long slide.
why? It's going to hold photos and so on. I can stop anytime.
Okay, fine.
Go fast because I just not do mathematics.
Yeah,
Like most
Yeah,
pictures.
yeah.
Here is a given like maximum of chi and chi coloring to give an upper point. Say chi is maximum. I can count the chi colors.
Yeah. So you need to color the whole graph with
Every copy of G, I can count the colors accordingly. Otherwise, I will be stuck. Chi is not greater than chi, then I will be stuck. Depending upon each class of H, I can count the same copy, the same set of colors.
so how to formulate and how to write. Suppose that is the idea, right? That is the idea. It's fine, but uh, how to write.
If I is a function going from one in chi g, then for one of the all the copies corresponding to vertices of particular color class of H, we will assign from 1 up till chi g. Then for second color class, 2 from chi g up to 1. Then
Yeah. So something like that. So you think about how to write, then you have to come here to explain all. Ready to explain.
Median edges. Right.
Pictorially you can explain.
Structure like coloring method I can explain.
Yeah, so you can explain.
So now H is chi-H colorable. So let these be the color classes. Now for each color class of H, I will now G Cartesian product H. Basically, I can imagine it as cardinality of H number of copies of H will be there. Corresponding to each color class of H, I will give particular coloring of G. Now G, all the copies of G are connected such that corresponding vertices only are connected. So first, for corresponding to C1 class, I will give the colors from 1 to up till chi G. Now, the vertex which is given color 1 here in C1, C2, the corresponding vertex will be adjacent. So that is why the vertex which is given to the vertex which is given color 1 in the first C1 copy of G, here it will be given 2. 3 onwards, chi G plus chi G comma 1. I am just permuting. The vertex which was given 2 in C1 now will be given 3. Similarly, so on. So the last one will be chi H plus 1, chi G, 1 to up till chi H minus 1. It is not from.
Is this clear? Or you need more explanation?
Consider G as the maximum product number. So first you are coloring U1 means with the same coordinate. Then so if U1 is adjacent to U, not adjacent to U, we can do the same color to UJ comma UJ, that copy of H.
Yeah.
If it is adjacent means we just like plus 1 to the chromatic number.
Yeah. So this modular concept you can actually bring. You think little bit more than I will try to explain. So whatever she said, some modular concept you need here for meeting. But can we say something, we define something and then we can say that it is basically going to fall in k number of independent classes, color classes.
Chi G plus chi H. So if chi H is less than chi G, then I. Chi G plus I.
Yeah.
Or I will from 0 up till chi H. For each color class here, I can do it.
Yeah, something like this. Let us try to see. So, if we are defining something, let us say U and V and U dash V dash. These two vertices are let us. For this we are going to see. Okay. So if you define something called, let us say phi is the coloring from basically 1 to like that, chi of G, and similarly psi is the coloring on H, 1 to like that, chi of H, and maximum is let us say maximum of chi G and chi H. Let us say this is, let us say K. Okay. Then you define over here something called phi u plus psi of v mod k, right? So now what will happen? If you think phi of u dash and psi of v dash mod k, right? Then what can you visualize over here? Can you visualize something over here? What? What will happen? Means in this case you can think of basically let us say u equal to u dash. The vertices are adjacent, right? Let us say when these two will be adjacent, if u equal to u dash and v dash is an edge of h, okay? Then what about the let us say this is my a and this is b. So what can we say about a minus b in this case? A minus b will be what? A minus, if you just take phi u minus phi of u dash plus psi of b minus psi of b dash, right? Sorry, total thing, right? Then this is nothing but psi of v minus psi of v dash, right? Right? And we are taking with respect to maximum. So it is basically modulus we are taking. So it is basically they are not equal. Means they are going to fall in different color classes. Right? So because of that, if these two are adjacent, u and v and u dash and v dash, then they are receiving different colors. Right? And this difference, how much it will be? In this case, this difference will be at most, you can say that chi of h, right? And the other case, it will be basically at most chi of g, right? Right. So one will be k since chromatic number is there, so you can zero and that thing you can see that this difference will be that one with respect to. So because of that, the chromatic number we are able to color the vertices with respect to using k colors only. That is maximum of chi g and I of h. So because of that, we can say that chromatic number of this thing is at most k, and already we have seen that it is at least k. So because of this thing, we can say that chi of this thing is equal to fine. Okay, another form of Brooks theorem. Let us try to see another form of Brooks theorem. So what Brooks theorem says, G is not Kn, or it is not a C2n plus 1, then chi of G is at most delta of G, right? So here suppose we want this thing, let us remove this thing. What is the degree of this thing? 2, right? So if we say that delta greater than 3, right? Can we say that chi of g is maximum of omega of g and delta of g, right? And suppose this thing can be also written as chi of g, sorry, this and omega of g less than equal to delta of g, then, right, then chi of g will be, right? Fine. So now question is what are graphs for which chi g is equal to delta g? Can you list all the graphs for which chi g is equal to delta g? C2n only. Are you sure? C2n is one example, you can say that. Okay. Is it easy to list? May not be. Okay. So now question is, can we make actually, if we are not able to list, then can we say that for this kind of graph, chi g will be at most delta minus 1? Or can we improve the, can we improve the Brooks, this is called Brooks bound. Can we improve the Brooks bound? So can we make chi g is at most delta minus 1? So in fact it is a conjecture by Borodin and Kostoska, and what is that? Is delta is greater than 9, omega of g is less than equal to delta minus 1, then chi g is at most delta minus 1, delta g minus 1. Or in the same language we can have chi of g is less than equal to maximum of omega of g delta of g minus 1. Here delta is 9. Okay. So question is what about this 3 to this delta value 3 to 8 or maybe 4 to 8. 4 to 8, what is happening? Can we bound by this thing, or whether it will be more smaller, delta minus 2, right? So that is our next question. Find graphs with delta G less than equal to 8 adjacent to 1 and 2 will be adjacent to 3. 3 will be adjacent to 1, 3 will be adjacent to 2, right? And this is adjacent to this. So what
Delta is
delta is 4. Huh? Delta is 4, omega 3, chromatic number is how much? 4. Okay. Yes, great. Yeah, this is one example. Okay. Huh? Whether this example will work for delta equal to 5?
faster than
So delta equal to 4, the conjecture is not true, right? Okay. What about delta equal to 5? Try to construct. Peterson. Chromatic number is 3, Peterson. Huh? Demonstrate what? Omega equals to 2 and delta equals to 3. Delta equal to 3. Okay. Equal to 3. Delta equal to 3 anywhere, that is Brooks Theorem, right? Here we have W less than equals to delta minus 1, but chi g is not less than delta minus 1. What W is less than equal to delta minus 1? Yeah, right. But chi g is not less than delta minus 1. Chi g is not less than delta minus 1. This is for delta equal to 3, okay? Delta equal to 5. anyone who can explain delta equal to 5? Okay, I am drawing the graph. You try to see. This is basically join this pink edge. Okay. Now let us put everywhere a triangle. Okay. So what will be the delta of this graph? Find delta of this graph, omega of this graph, and chi of this graph. This means triangle is joined with this triangle, and this triangle is joined with this triangle. Okay. What is delta over here? 8. So 3, 3 is 6 plus inside 2. Right? नहीं ऐसे होगा 3, 3, 6 and inside is 2. Right? So delta is 8. What is omega? What is chromatic number? Chromatic number is 3. You click the 6. So let us say we want to color this, and let us say here how many colors we need? 3 colors, right? The same 3 colors can we repeat over here? No, right? So here we need 3 more colors. Let us say here 1, 2, 3, and here let us say A, B, C. Okay. Here what we can do? The same thing we can repeat. Let us say 1, 2, 3. Here what can be done? A, B, C. Right? Then here again we need how many colors? 3 colors. Right? Different than 1, 2, 3 and ABC. Right? In this case it will be delta equal means omega chi is going to become 9. Right? Let us say here we are changing plus minus multiplication. Okay, these are the colors. Okay. Now with 9 colors we can do it, right? So can we do it less than 9 colors? Or maybe can we do it 8 colors? Try to color. Let us try to see this portion. 1, 2, 3, ABC and 1, 2, 3. Can we change any color here? There is no chance of changing any color, right? So here we can change the color. Now can we change here? ABC. Nine colors तो Brooks theorem को ये कर देगा, contradict. So it will contradict Brooks theorem. So can you color this? Yeah, by Brooks theorem we can color it by 8, right? But can you give 8 coloring? Which one? Here? No. Where? Here. 1 by plus. Okay. One by plus A by 1 multiplication by A. Now are you able to color? Right? Okay. So this is the counter example for to the conjecture for delta equal to 8. Right?
So if this to be a counter example, we need to show that it is not 7 colors.
Not 7 colors.
It can be colors with 7 colors.
It is not 7 colors also. You need to check. Can you color using 7 colors?
So minimum degree is 8.
So
Every letter should have 8.
minimum degree is 8. So whatever is the, let us say minimum degree, okay. I यहाँ delta is 8. Whether any delta is 2. 8 regular graph. Minimum degree is why you need for salary. How?
So can we follow the same trend again? Replace for the third one, replace 2 by minus.
Then whether it is 7, we using 7 colors, we can do it. Are you able to use with 7 colors? No, let him try.
So by following the same pattern, replacing 2
No, you check. After replacing, you check whether you are able to do so. You come and explain and yeah, this one and next question also. This lexicography.
I was greater than or equal to 10 by n.
Sorry?
I was greater than or equal to 10 by n.
Pi is greater than equal to n by r.
yes, that means
Pi is greater than equal to n by r power is n. N is 18. Alpha is 2. Right, 15 by 2. Right? So because of that, it has to be at least 7. 7.5 at least. That will be it. At least 8. Okay. So next question is
okay, so you can see this question number 1, the Reed's conjecture. Okay, let me introduce myself. My name is Dr. Uttam Kumar Gupta. So, you can see the Reed's conjecture over here. Let me introduce the Reed's conjecture more clearly. So, suppose this is your clique number omega g. We know the upper bound delta plus 1, that's a trivial upper bound by greedy coloring approach, and we can improve it to delta if delta is at least 5 and the chromatic number is below the delta. But Reed's theorem further says that the chromatic number is actually midway between this. This is, you can see, omega and delta plus 1 by 2. Okay. So basically this problem is open, and let us do the first part of this question. So we need to find the exact chromatic number of Catalin graphs C5 Kn, and that is a lexicographic product of C5 and Kn. So should I define lexicographic? Yes, C5 and Kn. Okay. So you can see the definition by yourself. What do we mean by lexicographic product? And basically, I am drawing just the graph C5 is K. So basically, this is formed by replacing. So as you can see, we have replaced each vertex with the clique Kn, couplet graph Kn, and this is the lexicographic product of C5 and Kn. Okay. So for this graph, we want to determine its chromatic number, and using this we want to prove that the Reed's conjecture holds for this graph, and that bound is tight actually. Okay. So what is the cardinality of VG? That's basically 5n. Okay. And what about the clique number of this graph?
Then
2n, right?
because
You can take 2 clicks over there. No?
2 copies of Kn are means each vertex of Kn is connected to the
What about the maximum degree of this graph?
14. Oh, okay. 2n plus 2n plus 1n plus 3n minus 1.
And what about the independence number of this graph? That will be 2, right? Okay, so we know that cardinality of Vg is at most chi g into. Okay, so this is a standard result, you know, and by this we know that chi g is at least cardinality of Vg by alpha g, and that will be what? 5n by 2. Okay, so the chromatic number of this lexicographic product is going to be at least 5n by 2. Now, if we can show that we can actually color this graph with 5n by 2 colors, then the chromatic number will be exactly 5n by 2. Right? So, how we are going to do that? How we are going to color this graph with 5n plus 2 colors? Exactly. So let us try to color. Okay, so suppose 1 to n colors will be used there, we have no choice. Okay, and after n plus 1 to 2n colors must be assigned to this, since this whole thing is a clique, right? Since this whole part, so this whole part is a clique, so at least 2n colors must be there. How many colors are left with us? We want to color this with 5n by 2 colors, right? And 2n colors are already used. So n by 2 colors we are having, additional n by 2 colors. So how we are going to do this? I think the idea of the previous question what sir have taught will work here. So anyone having an idea? So actually we can divide it in two cases actually. So first we will consider for n equals to even, and after that for odd we will do, first we are assuming that n is even. Okay. So what we will do, okay. So the half of the colors from this set we are naming set is S1, S2, S3. Okay. So half colors from this set S1 we will use in S3. Okay, we can use, right? Means you can say 1, 2, 1, 2 up to n by 2.
Yes.
And after n by 2 we are using some additional colors. You can say 2n plus 1 up to how much? 5n by 2, right? We can do this.
Yes.
And now what about S5? Again in S5 we can do similarly. We can take half colors from this set, just right. So how we will do? We will assign S5 as n plus 1 and n plus 2 and half, like 3n by 2, right? What? No. n plus n by 2 plus 3n by 2. Okay. And after that, half vertices are remaining, right? So which color we will use? Again, that 2n plus 5n by 2. Okay. So if you are adding these numbers, you will get n number of vertices over here. And now you can see that we can properly color S4 with all the colors available. Which colors are available? Actually, let me draw. Suppose these half colors are used in S3. Okay? And these half colors are used in S5. Right? So, now this color and this color we can use over. Okay, this is what we can do, right? So if I need to name the colors, so basically that will be from S1, what we can write, n by 2 plus 1 to n, and then from set S2 which colors we are using. Okay, 3n by 2 plus 1 up to how much? 2. So this one is actually I am doing this thing in general, so that's why it is a bit complicated. But what we are ultimately doing is just saving half amount of colors from. Okay, so this is a proper coloring of this lexicographic product using how much colors? 5n by 2, right? So now you can say that the chromatic number of what? C5 Kn is exactly 5n by 2, or you can say the seal of this. No need to seal over here because n is even, right? N is even. And now what we will do for n equals to odd? For n equals to an odd value, what we are going to do? So basically, for if n is odd, we will take one vertices from each set S1, S2, S3, S4, S5 and delete those vertices. Okay. So now all the sets means there will be even number of vertices. Now we can use the similar approach to color it with how much color? How much colors? So basically from each set we are removing one vertex, say U1, U2, U3, U4 and U5. Okay, so what will be the chromatic number of this? Right. So this suppose chi of G minus U1 to U5 will be how much? 5 of n minus 1 by 2. Right. Because the clique size in each, actually each set was kn, right? S1 was kn. Now all the sets have been reduced by 1. So we can do it with 5n minus 1 by 2 colors. Okay. And now what you can do, you can bring back all the 5 vertices and assign them 3 different colors. Because C5 is 3 coloring, right? So basically that means chi G is equals to 5 of n minus 1 by 2 plus 3 new colors, right? So what will be this? This will be 5n by 2 say plus 1 plus half, that means we can do this, right? So basically we can say chi G is equals to seal of 5n by. So for even and odd, this bond will work.
And bringing that, you are not going to have any issues.
No, we are assigning different colors, new colors, 3 new colors. Right? So for each case, we are able to show that chi G is exactly equal to 5n by 2, seal of 5n by 2. Okay, and let us compute the value given in the Reed's conjecture. The bound was actually delta G plus omega G plus 1 by 2, seal of this, right? So what was the delta G? Delta G was 3n minus 1. What about omega? Omega is 2n plus 1 by 2. So that value is what? Okay, so that means this lexicographic product satisfies the Reed's conjecture as well as the bound is tight.